conditional. Let's test some series. Okay, let us look at this first one. Let's see, it's got this -1 to the n power, so it's going to alternate in sign. Just taking the limit, you have 1 over the square root of n. Taking that limit is going to give you 0. So it's going to alternate in sign, decrease in magnitude, and have a limit of 0. Yes, this original series is going to converge by the alternating series test. But let's look at what happens if I were to somehow get rid of the alternatingness of it. And if I were to just have this thing, but it's always positive, let's see if that would still work. Let's see, if I take the absolute value, then instead of this top being plus or minus, the top is just always a plus. So I'd have something like this, which is a p-series with a p-value of 1/2. 1/2 is less than 1, so that guy is going to end up diverging by the p-series test. So the original worked. It was convergent, but when I made it bigger by taking the absolute value, this one did not work. It was now infinite. So I could say that my original series is conditionally convergent only. It works right off the bat. It is finite, but it's like just barely finite. If I make it slightly larger, now it's infinite, right? So just be careful. Test the original, then you test the absolute value. If they both work, it's absolute. If the first one works, but the second one doesn't, that's conditionally convergent. If the first one doesn't work, you're done. Diverges. There's no absolute or conditional divergence. That just is what it is. Okay, let's see if I can move this without scraping everything. Okay, I think we got 2 more examples on this page. Let's look at the one on the bottom left first. And I'm mostly still on the page. Okay. It says, which of the following series is absolutely convergent? Again, test the original. If the original fails, you're done. Then you test the absolute value. Let's see. That one looks like it's going to alternate. It's going to have a limit of 0, so that's good. That one's going to alternate. We literally just did this one, right? It was the same exact example. We know that one's going to converge by the alternating series test. The limit of this, look at it. If you have 1 over 1, this limit wouldn't be 0. So this guy is going to diverge by the nth term test. So that guy's done, right? That one's divergent. I know that one's convergent off the bat. That one's convergent off the bat. And it looks like that one's geometric. That one's going to work right off the bat. So now let's test the absolute value of them. If you kind of just ignore all the negatives, here I would just have 1 over 2n, where you could factor out the 1/2, and you just have 1/2, and then the summation of 1 over n. Well, that's the harmonic series. Half of the harmonic series is still the harmonic series. Having this extra coefficient doesn't really change it. The harmonic series diverges. So this one worked right off the bat, but then when you took the absolute value of it, it did not. So this one would be conditional convergence. But we were looking for absolute, so no answer on A. This one worked right off the bat. If you take the absolute value of it, remember we had the p-series, so it doesn't work. This one, though, the last one, here you've got the original works because of the alternating series test. Then when you take the absolute value of it, that one's going to end up working. It's geometric. The ratio is 1/2, so it's going to converge by the geometric series test. So the original works, and when you make it bigger, by getting rid of any of the negatives and making it all positive, when you make it bigger, it is still finite. That means this would be absolutely convergent. It's really pretty easy. Test the original, then you test the absolute value. Conceptually, it's a little bit weird, but I think you guys will be okay. All right, last one, and here's these multiple responses. Which of the following series are conditionally convergent? Ooh, so now it wants conditional convergence. That's great. I think it's got that same one that we did both in the previous 2 examples. So I know that one's going to work, right? That one works right off the bat because of the alternating series test. But then when you make it absolute value, it's a p-series, so it fails. So I know that one's conditionally convergent. So that's good. Let's go test the other ones. This is the alternating harmonic series, right? That one's going to work right away because of the alternating series test. But then when you make it all positive, you have the harmonics. That one works, then it fails. So that one is conditionally convergent. This one works off the bat because of the alternating series test, but then when you ignore the negatives and you test the absolute value, that's a p-series with the p-value of 3, which also converge. So this one would be absolutely convergent. All of them work right off the bat. This one still works, so it's just 1 and 3 that are conditionally convergent. Always read the question and make sure you're looking for the absolute convergent ones or the conditional convergent ones, right? There's a big difference. Sometimes they'll ask for one, other times they'll ask for the other, so just pay attention. All right, cool. Let's look at the last page for today, which is going to be talking about the alternating series error bound. And this is a little bit weird at first. And this formula and this stuff inside the box, this definition, seems strange, but it's really pretty easy, and hopefully I can convince you of that. All right, so just like with the integral test, whenever I do a partial sum, right, you add the first 6 terms together, you have the 7th term and the 8th term and the 9th term and all those other terms that weren't included in your partial sum. Remember, that's all called the tail or the remainder. When you add up all of those terms in the tail, that's your error or that's your remainder. So just like how we had the integral test and we had the integral test error bound, we are also going to have an error bound for the alternating series test. I want to know what's the maximum oopsies, what's the maximum mistake we could have been making for any arbitrary partial sum. All right, so let's read it, let's get confused, and then we'll talk about it and hopefully get less confused. Okay, if a series has terms that are alternating, decreasing in magnitude, and have a limit of 0, that means, yep, it's going to converge by the alternating series test. So it's going to converge, and it has some exact infinite sum s. Now, we're not going to be able to figure out what that exact value is, but we can approximate that infinite summation by doing a partial sum. And that partial sum isn't precise. It's going to have an error. It says that error, which you can think about it as a remainder also, that error is going to be less than the absolute value of the first omitted or the first truncated term. Seems a little bit strange. Let's read the box underneath. In other words, if 3 conditions are met, right, if it alternates in sign, decreases in magnitude, has a limit of 0, then you can approximate the sum by using the nth partial, or you can approximate that infinite sum by using the nth partial sum, and then your error is going to be the size, just the absolute value of that first unused or that first truncated or the next term. So if I add the first 6 terms together, the error, the maximum error that you could have is the 7th term by itself. Or if you add the first 10 terms together, the maximum error is the size of the 11th term all by itself. Let's conceptually go back and look to see if this makes sense. Let's go back, and I'm not going to need this one anymore, right, because that's all positive. But let's look at this. It's definitely going to alternate, right? We know this converges. Let's say, right, that whole list is the infinite sum. But it keeps going forever and ever and ever. At some point, we're going to see, okay, we're going to approximate that by doing a partial sum. So we'll say, hey,